Hi friends, welcome to the session 13. Let us continue our discussion. Today we are going to be discussing about control flow instructions. Okay, this is little different from what you have seen so far, and this is going to modify the way the program is executing, the direction, and the flow of the program will be modified based on these instructions. Okay, so we will see what are the instructions support this, and then what are the requirements for this from the higher level language perspective, and we'll see a couple of examples to understand how does it function. Okay, very good. So pay attention to this because this is something to do with the program counter, because these instructions are going to modify the value of PC, which register it is R15. Okay, so anything that touches this register we need to be careful, otherwise we will be taking the program to some other unknown location. So when you are writing this program using this instruction, because assembler takes care of it most of the thing, but you should be able to understand what is exactly happening, what the assembler the compiler generates, which instructions. Okay, so let us see what are the things we need to be careful about. Okay, now this session we will talk about why we need a program control flow, why do we need the control on the program flow, and then in specific to the control flow instructions, the normal thing what we look at, format and the data path, what happens inside the data path, that is inside the processor when this instruction comes into the processor, and then we will also look at the timing, that the number of cycles that this instruction takes, and then some usages of those instructions. Okay, very good. Why do we need program flow control? Okay, what is the default execution flow of a program? You know that this is a code memory, assume. Okay, and PC is currently pointing here, so you know that the width of this code memory is 32 bits, right? We are only talking about ARM state of the processor, not a thumb mode. So ARM mode. So in the thumb state, the instructions are all 32 bits wide. So the PC will be keep on incrementing to next locations, that is +4, and then as soon as this instruction which is in this 4 words come into the processor executes it, and then it automatically increments the PC, accesses the next instruction, and then this goes on. So you know the pipeline pretty well. So whatever PC is feeding, the instructions come. What is the first stage? By now you should know what are these stages are. Fetch. Okay, this is fetch stage of the pipeline, and this is decode. Okay, and this is execute. So the PC keeps on incrementing by 4, and then the instructions keep coming into the pipeline, and then processor executes it. So when it is executing a particular instruction in the execute state, it may take 1 cycle or it may take n cycles based on what kind of instruction you have executed, what is being executed. If it is a LDM or STM instruction which is multiple load or multiple store, it is going to take more cycles based on the number of registers are transferred. Based on what is transferred, it is going to take more time. So if this particular stage is blocked, it is very natural that these stages are also blocked. Okay, it is like a queue, you cannot dump a queue. Okay, so you have to wait, the instruction need to wait, not you, the instruction need to wait for the previous instruction which is occupying the stage to be completed. So this is very clear to you. I have explained this multiple times in different scenarios, so I am just trying to recall all that so that you are able to understand what is being discussed in this particular lecture. Okay, good. So sequential access you all understand. Now the program counter is incremented by 4, which I mentioned, and then it is feeding the pipeline which are the instruction words which are 32 bits wide. Now apart from the normal sequential flow of the program, we need a selection and iteration. Okay, these two are different kinds of programming paradigm, or not a paradigm, it is programming different operations that a program does. Okay, when I say program, we are talking about a high level language, either C or C++, Java, whatever language you know. So these languages support different instructions, okay, and you know that you can write a function and then you can call a function. Suppose this is a function foo in a high language in a main, okay, you are writing your C code. Then what do? You write this function. It will be in another file called foo.c maybe, and then this is another file which is called main.c is there. You are compiling this file and this file and linking them all together and then building a executable and then running it on a ARM processor. For our example, this whole thing is running on a ARM processor now. Now you are calling a function foo. Suppose it is accepting, this is written in this file foo.c. It is accepting an integer. Assume that it's a parameter. Okay. Now what happens? You will be calling it with some variable, in this case j. Then you will call this. Now what exactly happening? This whole C program has to be compiled, and then if it has to be run on an ARM processor, the compiler will generate some ARM assembly code. Correct? So for that, now what happens during the function call? Okay, the program comes here. The execution now, when you are suppose if you use C++, Visual C++ or Visual any of the development platform, if you are single stepping it and then you say that okay, I want to execute this and then I want to know what is happening inside the function. If you are single stepping it and then going into that, then immediately the control will jump to the first instruction in the foo function. Okay, inside that foo is there function, the control goes there. Then you start seeing that it is getting executed, and then when the function ends, it comes back and then start executing from the next instruction. Maybe here I++ is there, it will execute this instruction. So what exactly is happening in the program, in the assembly code? This call of a function, okay, it is supposed to call a function from this. So this will be replaced with one set of instruction which we are going to talk about today. So that instruction takes the control of the processor to some other location where this program is loaded in the memory. Now when I say it is taking a control, what does it mean actually? It is actually taking the PC value. Normal flow, the PC would have got incremented to the instruction which may be a small C code here, which could get expanded to a set of assembly code. So it would have executed this instruction in a normal flow. PC would have got incremented by 4 and then it would have got it will be executing all the assembly code which was generated by the compiler. But when a foo is called, a function is called, then the control goes here and then it is going to, PC is going to access every assembly instruction which was generated by compiling this C.file, foo.c. It would have generated some obj and it would have compiled and then combined together and linked file would have been created, and then that is code is sitting in the memory, core memory. So now we are going to see when you are having such a control flow happening, changes happening in the program order, the way it is getting executed, how is it implemented in the assembly code. Okay, so there should be a support by the processor for compiler to generate that code so that these kind of things can be done. Okay, see, finally whatever C code you write is not going to be executed. What is going to be executed is the set of assembly instructions. So there should be a support in the assembly code to enable this program flow so that the R15, the PC register is modified accordingly so that you get the same feel of what the original programmer intended to do in the C code or C++ code, whatever high level language. So our focus is going to be how this is done. Now tell me, you might have seen all this in your high level language. So if some condition is true, execute this, otherwise there is no else here, so it will just fall through that. Okay, just to refresh your memory, if suppose I is greater than 0, this code what you have written I++, okay, has to be done. If this is not true, then execute whatever is written here in the C code. Similar things should be done in the assembly, so that you have a whatever is intended here is executed by the processor. Okay, so it is one form of representing what you are interested in performing, and assembly language is the same thing is converted in this language, so that processor understands what it is supposed to do. Okay, the job of the compiler is to do this. So now you will not see if or else in the assembly code. Okay, you won't have if instruction in the assembly code. Similar, this whatever is seen here is converted into a set of assembly instructions which implements this particular intent. Okay, what the programmer wanted. Very good. So maybe program there are some constructs like if this condition do this, else execute some other set of instructions. So if this is true, only this set of instructions should be executed and this should not be done. If this is false, then this should not be done and only this should be done. So this kind of conditional statements need to be executed in the assembly. So what are the support needed for that? So when I say a set of instruction, that means a small few lines in this, suppose 5 lines of C code you have written, that would have been transferred to some 50 lines maybe. I am not saying that it is always plus into 10, but that it is in terms of some n. Okay, certainly it will be more than number of C instructions that you see in the code, which when it is converted into assembly, there will be a set of huge number of instructions. Now they will be starting from some address 100 and then it will go up to 200. Assume. Now you are saying that if this condition is true, maybe 0 is set. Okay, I want to execute this. Otherwise, I want this to be executed. Now, how can you do it in assembly? You have to put some instruction to say that if it is 0, you execute this. Otherwise, jump to this instruction so that it falls through this. Now, suppose if else you have put in this case, what happened? Even don't if you execute this, after this you jump here. Otherwise, come here and then execute it and then come here. So it could be if else or if then. Anything needs to be communicated to the processor through assembly language. Now this you understand. And while loop. So you might have seen lots of code written in C or C++ where it says as long as I is greater than 0, do this set of instruction. Okay. So when you see this, after this execution, what happens? You will be incrementing I plus plus, or in this case I am saying if it is greater than 0, you do it. So if the loop has to be terminating, so it should be sorry, what I mean by this, I minus minus you should do. Okay, so you are initializing the I with some 10. Okay, and then as long as this is more than 0, you keep increment, keep doing this instruction, and then it is decremented once in every iteration. So you don't see that the control coming here and then checking this condition and then following through it. But when you are converting this particular C code into assembly, what you may have is some assembly instructions, and then incrementing will be replaced by, in our case, add whatever I is there, or if because it is minus minus, maybe it's a subtract. Subtract instruction will be done, and then it will check branch if it is equal to, okay, this maybe where this particular instruction is starting, label is maybe L1 suppose. If 0 is equal to 0, you do not jump, so NE, okay, suppose it is converted into branch NE L1. What does it mean? I is decremented, and then if it is not equal to 0, you come to L1, otherwise fall through that. So effectively this while loop has to be converted into assembly instructions which will perform this job. So even the same thing is true for loop also. So when you have such instructions in your C code, when the language has defined such a constructs in the programming language, assembly needs to support them. Okay, so let us see how they are implemented in our case. So basically these instructions are PC modifying instructions. to support those high level language constructs needs support by the assembly language instructions which can change the flow of execution. Now the flow of execution can be changed if assembly instruction modify the PC. That is very important. PC is what? R15. Now PC modify instruction can be of two types. One is unconditional. What does it mean? Always you jump to that particular. Where will you have this kind of unconditional jump? When you have in a high level construct. Suppose I will tell you for loop you have, okay, inside that. Now you suppose here you are saying that break, okay, you have put a break condition, a break instruction, okay, in the C. What does it mean? If the control comes here, it is supposed to come out of the for loop. Maybe when it comes out of the for loop, it has to come somewhere here. So whatever is the instruction which are generated specific to these high level languages, that address should be given for this control to come here. That means this is the branch to this label. Maybe assume that this is L2, then as the compiler would have generated a code to say branch L2. If your control is coming here, please go to L2. This is unconditional branch. Okay, it is not checking, the break is not checking if is there or inside some condition is not there. So it is a unconditional branch. If there is a if then else, it is a conditional branch. Okay, so that's what I am calling it as a unconditional or conditional. Conditional branch always checks some of the flags. So how can the processor know if I is greater than 0 or less than 0? All those conditions it will do a compare or subtract or add some arithmetic operation it will do, and then it will make one more thing you have to remember. Okay, compare if it does anyway the flags are affected automatically, so you don't have to worry about it. But when you are writing these instructions, suppose not you, maybe a compiler is generating, it will remember to put the S there. Okay, if you recall, these instructions default do not impact the sequencing these flags. So the compiler has to take care. Suppose if it is going to look at these flags based on this instruction, it should put the S there, so that this instruction affects the flags, and then it takes a based on this flags it will take a branch to some other location. So this is called conditional branch. Okay, let us see. Now I have not told you what are the instructions that support this. So let us see. This is the instruction. Okay, how do you write it? This is B. B stands for branch. Okay, L is optional because it is within the parenthesis. If L is mentioned, let us come to that later. Assume that B is the condition. If this condition is true, maybe the branch instruction also can be. You can add the condition inside, and then what will be here? It will be a label. Okay, label means it's an assembly label. Okay, in the assembly instruction, a particular instruction will be associated with some label, and that address will be computed based on this instruction. Now, how does this particular instruction help in computing it? Okay, actually, what you still remember, this is 32-bit wide instruction. So you cannot have an absolute jump with a 32-bit address. Okay, it has to be a reduced number of bits allocated per offset. As much as possible, they have given 24 bits here. Okay, now I will remember this. Then we'll go to the next slide, and then I will explain you how this offset is modified. Okay, how it is computed. We will come to that. Okay, some offset is computed. Who computes this offset? It is done by based on the compiler or assembler, whoever is computing it. They look at the label and where it is located, and based on the address it will generate the offset. It will compute this offset and then generate an instruction by fitting in this offset in this particular bit positions. Okay, we will see some examples, then it will become clear to you. Now let us talk about L. L is another indication to say that when you are branching, okay, when the processor is branching, let me give you an example. Suppose BL L1 is a label. Okay, now L1 is here. Okay, set of instructions are there. Now if suppose if you are calling in the original C program, you are calling a function, then what happens? When you are calling a function, the control should go to the function and then it should return back. You remember? It should return back to the location which is below this instruction, which actually took the control to the function. I am calling this as a function. The function is starting at L1. So the control should come back to the instruction which is below BL. Now how can it be achieved? See, once the PC is modified, okay, by adding this offset or subtracting this offset from the current PC, okay, and then the control comes here, the processor doesn't have any means of finding out where does it have to come back to, okay. It doesn't know. This PC is lost, it is overwritten. When I say PC's offset is computed and it is control is coming here, it is very implicit. It is very obvious that the PC value is overwritten. So that register value, whatever is holding the address, the R15 is modified. Now what happens to that? This address is overwritten with this address, and then it will keep on executing it by incrementing it by 4. Now how will it know where to come back to, which address to come back to? So to inform the processor, we need to store that value somewhere. We mean the processor while executing this instruction, it should make sure that the address to which it is supposed to come back should be stored somewhere, so that the control can come back. So ARM processor supports it with the help of reserving a register for that purpose, which is called a link register. Why is it called link register? Because it is linking the function with the callee. Means caller and callee. If you are knowing about this, somebody is calling another function, and then this function is linking back to that caller by storing the value or the address to which it is supposed to come back. So where will you store? Because R14 is modified, so it has to be stored in some temporary register. So the processor doesn't insist that you should store it only in R14, but if you are using this instruction, it will certainly be stored in this location, but you are free to do it by using some other registers also, okay. But assume you are using a BL instruction, then it will automatically save this value into R14. Which value? The address to which it is supposed to come back to. Now how will you make sure that it comes back? Who does that? That is also be generated by a code at the end of the function. It's some code has to be written which will copy, okay, this whatever value is there in R14 into PC, okay. So it cannot come back automatically. Some assembler or a compiler has to generate a code which will copy the R14 value into PC so that the control comes back. I hope this is you are able to follow, but I will show you some examples so that it becomes clear to you. So to explain this, I am giving you a background of what is happening in the processor. Okay, so if you are using a BL instruction, automatically the address of the next instruction is stored in the R14, and then the control jumps to the wherever the offset points to, okay, wherever it takes to. PC is modified. Let us see an example, then it becomes clear to you, okay. Let us move to the next slide. So branch jumps to offset address given with the instruction. If you have mentioned just a branch label, okay, some label, then this instruction just goes there. That means what? PC is modified to point to this. So in this case, the R14 is not affected. Please remember, only when you say L it will be affected. So that means what? You are not, or the assembler or compiler is aware that the program is not interested in coming back to this next address, okay. So it doesn't have to bother about where is it jumping from. So it is it is going there, but without bothering about whether it has to come back or not. Suppose if the code is like that, you have a one-way jump, but you are not. It's not a call to a subroutine or a call to a function. So you don't need to bring the control back to this address, okay. So in that case, what happens? BL is not used, B only is used, and then the control goes there. So R14 is not used by this instruction. Okay, please remember that. Now, branch with link. If you say this, then what happens is the old PC value. It's not an actual old PC value. This is a PC value next to the current BL instruction. Okay, that is what we are calling it as a old PC value. Suppose BL instruction is at 100, the 104 will be stored in the R14, so that when you copy that R14 into PC, the control comes here. Okay, it will not come automatically. It has to be brought back by copying R14 into PC. Okay, very good. Let us go back. Okay, so the PC value written into R14 is adjusted. Why it has to be adjusted? What I mean by adjusting? Let me explain. Again, I am bringing back the pipeline. By now we should know that, but still let us see. I am now font of 100. So let us see. Here, assume that I have put a BL instruction to L2. L2 is what? At some 200. Okay, this is the address 200. Assume that all the addresses what I am writing is all in hexadecimal. Okay, so that you dot is there. Please remember, there is so much of memory I can't draw. My screen is only limited to this size. Now remember the pipeline. Now see, always when you look at any instruction, this pipeline should be at the back of your mind. Okay, what is this? F. I will not say what is F and what is D and what is E. Okay, now what happens? When will the BL get executed? When the instruction is here. Is it correct? Now when this instruction is here and getting executed, that means what? What I mean by getting executed? It has the offset which has come along with the instruction, whatever is the value. Okay, it has come along with the offset. It could be plus or minus. What will this do? It will add this value with the existing PC. Okay, plus or minus offset it will do, and then write that value into PC. Now apart from that, it is supposed to do one more thing. Whatever is the address, that is 104, should be copied into R14. Correct? Because I said BL is getting executed, so it is a branch with a link. That means BL is located here. So whatever is the offset, it is which will compute the PC to 200, and then it will start executing whatever instruction here. Don't bother about how will it come back. We are not worried about that right now. I am only explaining you what will the PC do when it is supposed to store this R14 value. The correct value which is supposed to be the instruction which is next to BL into R14. I said that something has to be adjusted. Why? Come back to PC, the pipeline. Okay, which instruction will be here? Whatever instruction here. Okay, X whatever, and this is 108. Which instruction will be here? Whichever is at 108. You agree? Because when BL is here, the next plus 4 will be here. It should have got decoded here, but the next instruction is getting fetched and then it is sitting here. Now what is the PC value at this moment? When this BL is computing this offset, adding that offset, what is the value of PC? Is it 100 or 104 or 108? It will be 108 because you just saw that it has fetched this instruction. So PC will be that only. After this cycle only, the auto incrementer in the data path increments the value and then initialize it with the next address. After this execute, this instruction goes out of the execute state. So the PC is actually 8, and you are computing some offset to go there, but you are supposed to save this some PC value which is next to this BL instruction. That means it should not save 108 into R14. You agree? If it saves 108 in the R14, the control will come back here. If somebody copies the R14 into PC, the control will come back here, but the control should come here. because the instruction next to BL is this. So it should subtract 4. Okay, basically adjusting means subtract 4 and then keep this address in R14. Okay, and then it should add this offset or subtract this offset and then come to the next location. In this case, it is supposed to add that offset and then come and execute this instruction. Now, can you realize that when this jump happens, what happens to the pipeline previous stages of the pipeline? The X and Y are here already, but they are not supposed to be executed now because the BL wants the control to go here. That means the instruction here, maybe you call it as A, B, that should come here into the pipeline. Okay, so what effectively happens is this will be flushed, 2 cycles are wasted. Now A will start moving into the pipeline. First it will come here, and then after that A will move here and B will be here. After that A will come here and B will come here. Maybe if there is another instruction C, that will be sitting here. Okay, this is a kind of pipeline happens. So please remember, when you are flushing the pipeline, don't think that A can jump here and then start executing, skipping these 2 stages. It is not possible. Until the fetching happens, until the decoding happens, an instruction cannot come into the execute stage to get executed. So there is no shortcut. It has to go through this. Okay, different stages it has to go through. So effectively 2 cycles, the 2 instructions which were there will get emptied and then the control flows here. So this is what I mean by adjusting. That means R14 should be copied with the address which is next to the BL instruction. Okay, in this case BL is assumed, so I am saying because R14 will be modified only when you use a BL instruction. Okay, good. I hope you understood this. Note that the CPSR is not saved with the PC. If you guys are aware of x86 processor, okay, some of the instructions, okay, especially when it is an interrupt or there is a call assembly language in x86. So there are some instructions, okay, in x86 or in some other processors also, which will default save some CPSR also if it is required. Okay, but please remember there is no implicit saving of CPSR when there is a branching happens in the ARM processor. So you don't think that it will be saving it. Okay, if you need to keep that, you have to save it yourself. Otherwise, you will lose the value what was there in CPSR. Now R14, inside the R14, after this address is saved, okay, after this is done, inside the R14 1 and 0 bit, that means R14 you know is a 32-bit register, right? So it will have 0 to 31 bit, right? So 0 and 1, what are these bits? They are the lower 2 bits of the address. Which address? Program address. Please remember this is the program address, code address. Now code address changes in a 4-byte ball. It is aligned always 4-byte aligned, and then it gets incremented by 4 always. Okay, that means the address 1000, our favorite 1000, is the first instruction. Next instruction will be at 1004 only. Can there be any instruction between these 2 addresses? Can it be 1001, 2 or 3? It cannot be. You agree? If you get only from 1000 you jump to 4, from 4 you jump to 8, means jumping means the addresses change, keep incrementing by 4. That means the lower 2 bits are always 0. Correct? If you change this bit position, it will be 0 0 0 first, and then 1 0 0 4. 8 is 1 0 0 0. C is 1 1 0 0. So you see that lower 2 bits are always 0 because it's at 4-byte aligned. Because of that reason, because you are writing something into the R14 now, it always makes sure that this 1 and 0s are always clear. Okay, because there are 2 bits reserved for that position in the register, so that will be 0. Now to return from the routine called a branch with a link, now I am coming to the place where how will you come back from the subroutine. remember you went to L2, okay, the you jumped, sorry, I'm saying you are not jumping, actually the processor is jumping, sorry about that. Okay, now BL L2 is we said it came here, the processor control came here, it starts executing. Now I told that this address next to BL is saved in R14. Okay, you also know that it is done. Now wherever this function ends, suppose it should write some code for this control to come here. What is that code? That is what is given here. You know that PC can be used as a simple RD in the move instruction. So you, when this adjustment is already done, okay, which is pointing to the instruction next to this, it is very simple that you can come bring the control back to this particular place by just copying R14 into PC. You agree? So this is what will bring the instruction, the control back to this location. Okay. So what is given here is the instruction, this instruction. Okay. This is how the control comes back to the location which was saved in R14. Okay, prior to the BL instruction. Okay, good. Now there is another way also you can do. You know, by now you are familiar with the LDM. So suppose when you were going to another subroutine BL, this is a subroutine, then you went took the control to L2. You know that there are some instructions here which you have written as a subroutine, and then you will be using lots of registers, right? R0, R1, R2. There are so many registers you are using here. But in the original code, in the original flow also, you are having instructions which are being used. Now, if the control comes here and then it modifies some of these registers which was changed here, and then you come back by executing this instruction, either move or LDM instruction, you come back here. Will you have the values which were before this? You will not have it, because if you have modified them in this subroutine, you call it as a subroutine. Suppose you are calling a function which is which is using some registers. So in that case, what you are supposed to do is you are supposed to save the registers which you are going to be using in the subroutine, and then recover, copy back those registers, okay, just before coming back, so that you get the same state of those registers that was there prior to this BL instruction. To achieve this, you have to use LDM. You have to use STM here. Okay, store whatever registers, you will mention it in the register list. Okay, to stack somewhere in the stack. You know that maybe R13 you may be using as a stack pointer or any other register. You put them into the stack. Suppose it is going downwards, you keep on putting them. Okay, and then when you are done with your function, you will be writing an LDM to say copy back the same set of registers, so that the stack comes back here, and then you do a LDM PC. That may in this PC, what will you do is you will write R14. Okay, that means the PC value is copied. The whatever is there, the stack, stack. You will be saying that which is actually stored in R14. Because suppose your R14 is saved here. Okay, this register. That R14 you will be copying into PC, so that you come back to this location. So the PC is restored by using a stack instruction. That means LDM. Okay, because you are saving that R14 in the stack. Otherwise, you may not have saved it. Then you have to take care that R14 is not disturbed in this function. Okay, that is very important. Then only this not be overwritten. So please remember, whenever you are writing assembly code, you are supposed to take care of the instruction, the register contents, if you are expecting it to be maintaining some continuity in your program. Okay, done. So we have taken more time here. I hope this is all clear to you, so that next few things we can go faster. So offset is computed. Now offset is 24-bit, I said, because 24-bit only is possible for the ARM instruction to reserve. It has reserved all the 24-bit. Now it is shifted by left 2 bits. Why? See, when it is saved, suppose you are supposed to No, you know that the bottom 2 bits are always 0, right? I mentioned to you that this 1 and 0, the bit 1 and 0 of the address is always 0 inside. So you don't have to save this 2 bits while computing the offset. What you do is, suppose whatever address you will get by adding this offset, that offset itself you save it such a way that only the higher 24 bit is saved and the lower 2 bits are recovered by shifting it left. Okay. So what exactly happens is you get a 26 bit wide offset actually, because it is all 4 bit aligned. So you are 4 byte aligned. So you are very clear, you are aware that these 2 bits are anyway going to be 0. So you can accommodate more number of offset values if you save only this part of the offset. Okay. Anyway, this will be 0 because all the addresses are always 4 byte aligned. So that's why you see that it is when you get the offset from the instruction, the processor, when it gets the offset value, it actually shifts that by 2 bits. So you remember that when the assembler is putting it inside, it should shift right and then store it, and then the processor will internally shift it left by 2 bits and then recover it. Okay. So that way your 2 bits are saved so that more offset can be given. Now you may wonder why this offset should be greater as far as possible. Why? I'll explain you. Suppose this is where your program BL is there. Okay. Currently you are executing this. You are willing to come back to this with the R14 saving this. But from here, how far you can jump? How far you can make the processor, okay, minus offset and plus offset. How far you can make it go decides about, okay, how much instruction, how big the instruction could be in the code memory, and then how far you can reach them. So the processor will try to accommodate as much as possible. So it has done its job. ARM processor, they have accommodated 24 bits, and then they have also given you another 2 bits of advantage. So maximum 26 bits of offset can be stored, not 32 bit of offset. If 32 bit of offset is there, the whole range could be covered. Remember, if you see the whole code, code memory, including data and code, the whole thing is 32 bit wide, right? That means plus or minus, suppose it is in the middle, plus or minus 32 bit in the middle. If it is here, it should jump even more than that, right? So if it has to jump the whole memory area which is available, it will need at least 32 bits, or even maybe 33 will make it clear, come here. But you are limited with the 24 bit and then additional 2 bits, so 26 bit offset. So this processor can jump only 32 megabytes, plus or minus 32 megabytes. I want you to verify how by saving and having an offset with the width of 26 bits, okay, plus or minus 26, you have only 26 bits to represent the offset in 2's complement form. How can you get a 32 bit byte of megabyte of offset? Okay, so it can go for as far as possible. That is, the maximum is plus here minus 32 by megabyte, and this is plus 32 megabyte in the code memory. It can jump. The control can go. So that is what is done here by this particular instruction. So the offset is taken and it is plus or minus is done. Now how will it know whether it is plus or minus? There is no bit anywhere stored here to say it is a plus or minus. This offset itself is stored in 2's complement form. Please remember. So what does the processor do? It left shifts it by 2 bits, right? That I told you. Maximum it will accommodate 26 bits. It will become. Then it will sign extend. Please remember, sign extend. If it is name, it will be all 1. If it is MSB 0, all 0. It will sign extend it up to 32 bit, and then now it has got a maximum 2 or 2's complement to offset value, which will be added with PC, whichever is the current PC, to compute the new PC value, and that will be written back into PC again. Okay. Please remember, this is what is happening when the assembler or the compiler has generated the offset. This is what the sequence of operation. It will be shift left by 2 bits, that means this will be 0, and then now you will get a 26 this 26 bit value you will get, and then you do a sign extension to 32 bit, so that any operation within the processor is 32 bit wide. So this offset is also made 32 bit wide as signed value, okay, 2's complement value, and then it is added with the current PC value, and then the control goes to P. So then PC is modified, then control naturally goes to this location, new location. Okay, very good. Now I am sure you will be very clear. Now this is what I mentioned to you. Okay, so this I have already told you. PC will be 2 words ahead of the current instruction. This I explained to you already. Now suppose if you have written a big code and then it has to jump to beyond this 32 megabyte. What it is supposed to do is it should use a previously loaded register. Maybe it could have written the offset into some place memory, okay, the 32 bit value, whole 32 bit value, and then it can do a load. If you remember pseudo instruction I said LDR, ADR I mentioned, right, ADR in the last session. So address calculation, this ADR instruction, what does it do? It will compute the address. So it could be in another memory location also, that whole 32 bit offset can be copied and then added with the PC. Okay, so if it is not possible to if the jump is farther from 32 megabyte, it has to be done by previously loaded value into a register or from a memory copy and then modify the PC accordingly. Okay, good. So these are all not to be done by us, by the tool, but still you should be knowing what actually happens. Okay, now is the interesting part of the instruction. Okay, how does the BL get executed? Now by now I think based on whatever I explained, you should be able to clearly understand. PC is coming through the A bus, okay, PC value, which is the current PC value, and then offset is coming from here. Why should it come from here? It is not sitting anywhere in the register. Okay, please remember, offset was with the instruction which was decoded, fetched and decoded, and then passed through a pipeline register. If you remember, between the stages there are pipeline register which carry the information about that particular instruction. So it is passing on the offset value which was read by the instruction along with the instruction, that is coming through this backdoor entry. It comes to the barrel shifter. Automatically it knows if it is executing BL, it is supposed to do a left shift, logical shift left, okay, by 2 bits, because you know that 24 bit has to be made into 26 bit. Okay, originally 24 bit offset is only written into the instruction. So 26 bit, sign extend it, inside automatically the sign extended value will be going into this. Now it is just added. Why it is just added? The positive or negative is based on the offset value. Okay, B will be either positive or negative. So you have to just add along with the PC value to get the new address where the control has to be going, and it is written into address bus. Now tell me, what is this address? This is the new, that B1 or L1 or L2 whatever I mentioned, that address is written into this, which goes into the address bus to fetch the instruction, the new instruction. Got it? I hope this is clear to you. Now let us come next cycle. In the next cycle, if suppose it is a BL instruction, please remember, if it is a BL only, this job will be done. If it is B, this particular cycle will not be there. So I am explaining for BL. I have put both here, but please remember, this is only meant for BL. Why? Copying into R14 happens only with the BL instruction, branch with the link register. So what is it supposed to put it? I said adjusted. If you remember, that adjustment is not done here, it is done in the next cycle. But whatever is the current PC value, what is this PC value? Let me come back again to the example L2. Okay, assume that this instruction is at 100 and L2 is at 200. If you remember, that is what I said. Now the 200, the new address has gone here. Okay, please remember, 200 has gone to the address register and the new instruction is getting fetched. During that time, the next cycle, even after the one instruction, the new location is fetched, next cycle still the PC is still fresh with the value which is actually 108. because it is plus 8, right? It was actually fetching this instruction, right? So 108 is there in this register PC. It is still not modified with the 200. So this 108 comes here and gets written into R14. Okay, the same value is written. There is no adjustment possible here because you see that it is equal to A. What is written into is whatever comes on this bus. What will come on this bus? Whatever is stored in R15. R15 is right now 108. So 108 first gets written into R14. Okay. While the instruction gets incremented by 4 and the next instruction gets accessed. Here 204 goes out. Remember, originally here 200 went. In the next cycle 204 goes. That instruction is getting fetched, but still your PC is still R14, which is getting entered into R14 now. Now you may wonder who will do the adjustment. Okay, let me explain you. In the third cycle, okay, remember in the third cycle, after this cycle is done, in the third cycle what will happen is this R14 will come here, and then this will be programmed. ALU will be programmed to -4. Okay, it will do -4, and then it will write back that value. R14 will become which one? 104, isn't it? Correct. 104 will be written into R14. Okay. It is not PC. Okay, please remember in the third cycle it will be R14 will be copied and then written back into R14. Okay, same R14 comes here, which is 108. Subtract by 4 -4 and then 104 you write back into R14. At the same time in the third cycle what will happen? This incremented value will get written into PC. So PC would have by now modified to the new location 208 or whatever. It would have got changed, but this now R14 preserves the old PC value. Okay, that's what I said. PC is also updated with the new 200, that 200 plus, maybe 204 or 208 based on which cycle we are in. That will get written into PC, because that can be written parallelly because PC has a separate read and write port, and then the rest of the registers have to read and write ports, so it can happen in the same cycle. So that's what happens. So I hope this data path is clear to you. Now this will be very obvious. Okay, this will be sequential cycle. This is also a sequential cycle because it is next instruction only. But will this be sequential? Though the same fetching is happening, the new instruction is getting fetched from a new other location, so it has to be a N. Please remember. Okay, and then afterwards it will all be yes. Now how many cycles that branch with link or branch takes? It takes this many cycles. What are they? 2s and 1n. 2s and 1n is the number of cycles it takes. So I hope you will be able to compute this on your own. Okay. Now let me ask you to take a 5 minutes break, not to go out of the class, just to look at this instruction, discuss with your neighbor, and then try to understand what is happening here. Okay, I have given some comments also, so that you won't be totally surprised with what is happening. Please spend some time, understand this. Okay, let us get back. You can rewind it after 5 minutes. So 5 minutes break. Okay, welcome back. I think I don't have to explain now because all of you would have understood it. Just for the continuity sake, let me tell you. This is what? Just a branch. Does it affect R14? No. R14 is not touched by this instruction. Where does it jump to? This location. Now I will leave it to your experimentation. Okay. What will be the value of offset here? If you can guess the offset value, then only I will say that you have understood this fully. Okay. Though it is not your job, assembler compiler will take care of it, but knowing this is better. So when whether it's a simple branch or a branch L, the offset is same. Okay, please remember, whether it is just a branch or a branch with the link register, the offset whatever is computed is same way, which is depends on the label where it is going. but based on L is there or not, this next instruction, whatever is the next instruction, gets saved into R14. Okay, please remember that clearly. So in these two instructions, one is just a branch, another one is branch with the link. So what is the offset? I will explain you, maybe explain one here. You can compute the offset here, and then you can feed the same set of instruction in your simulator, and then try to see what happens there. Okay. So tell me, what is the offset the process the assembler is supposed to put in the instruction? The PC, current PC is 1008, which that is the instruction where the B is there getting executed. But during this time, when this branch is in the execute state, where does PC point to? It points to 1010. Where this particular label points to, fortunately or unfortunately, it is to the same location. Please see that I written B sub here and then written this code. So it is nothing between these two. Okay, this is the address this B sub is pointing to. So effectively, whatever is the incremented PC value is where the particular jump is supposed to happen here. So when the compiler or assembler generate this instruction, it will make sure that the offset value is 0, because it knows that PC would have been already pointing here, because PC plus 8 is this, and your jump is also happens to the branch is also happening to the same location. So PC need not have to be modified, it just has to be added with 0, but you have to mention some offset. So you can also mention the offset as 0, which will actually correctly point to the location where it is supposed to go. Now tell me what happens to this. When this BL is done, immediately it comes here and then it executes another BL where it saves this address in the R14. Okay, R14 register will have the value exactly 1014 it will have. Okay, I want you to run this code in your simulator and check every content. Okay, but the control will come here first. Okay, when it comes here, you can check R14 is modified to this value or not. Okay, now what is the offset it will compute? The PC will be here actually plus 8. So it has to add this 4 and another 4. So plus 8 has to be added. So what will be the offset stored here? Will it be plus 8 or will it be plus 2? Please think it over. If you recall what I mentioned, offset is not the exact offset, it is a right shifted value 2 bit to the 2 bits. Okay. So originally offset was computed to be 100, but it will right shift it by 2 bits to make it just 10, which happens to be a 2. These are all zeros, right? So offset will be stored as 2 in this location. Offset will be 2. Now how will it come back to proper value? You know that the processor shifts it to the left by 2 bits so that it will get back that value originally, and then it will add it with the PC so that it will come back to this location. Okay, understand it? It is very important. Now tell me, this will be executed, then what happens here? R14 I told this value is there, so it is copied into PC, so control comes back to this instruction. It will get executed after that. Then this is the software interrupt. We will talk about this instruction later on. This takes the control back to the processor. So this is what happens in this. Okay, if you understand this and if you can find out what is the values of offset computed, you are an expert in branch instructions. Okay, good. Now branch with exchange. Okay, what is this? Normally when you say exchange means we are exchanging values. Okay, I exchange money with you means maybe you are exchanging money with the shopkeeper. Then what do? You give money to the person, you get some item back, right? That is what is called exchange. But here this exchange doesn't mean that. It is exchange means it is not two-way. It's a one-way actually. What does that mean? Suppose I have written a code, instead of BX or B or BL, I say BX or 0. Okay. So what it actually means is the PC, whatever is the PC R15, okay, is copied with the value which is there in R0. R0 is what? One of the registers. R0 to R14 can be used for this purpose. Okay, please remember, you cannot write R15 here. You can't say I want to exchange my PC with my PC. Okay, it is illogical. This is not allowed. Okay, other than R15, you can say that I am interested in exchanging the value what is in some register with a PC. See, effectively this could be done with a move also. Okay, move PC comma R0 also does the same thing, right? Here the BX code has some more intricacies to that. I will explain to you. So it is little different from move. Okay, it is not just moving. Okay, it has got some other meaning also, but I'll explain that BX. Okay, now BX does this job. It exactly copies the value in R0. Okay, now does it copy everything? No, doesn't. It copies branch causes a, okay, first of all let me explain you what does the branch causes. If the pipeline fetch happens and then no new instruction get fetched, all that are same. It is the same as what I explained to you earlier. Okay, this also takes the same number of cycles originally as B and BL. Okay, just hold on, I will tell you the difference as I explain this. R15 is used as an operand in the, if it is you are trying to say BX BX, please remember it is only one single operand. Okay, you cannot write BX R15. Okay, and this instruction also permits the instruction. I said permits the instruction set to be exchanged. What I mean by instruction set exchanged, I need to again remind you of two modes, though I have yet to touch upon the thumb mode here. Okay, but this instruction cannot be explained without bringing that thing to you. Okay, at least for a moment and assume that ARM mode is whatever we have seen so far. Thumb mode is something little different, which means that it actually assumes that 16-bit wide instructions are saved in the memory. Okay, in the thumb mode, whenever the processor is running in thumb mode, what we mean by that is, I told you earlier also, just I am recalling that it just accesses 16-bit at a time. Okay, it could read 32-bit and then internally organize it, but actually every instruction is only 16-bit wide. Please understand that is a different mode. Now, how will the processor is communicated? Either whether it is accessing a 32-bit value or 16-bit value based on a thumb mode bit in the CPSR register. So actually this BX instruction is used for informing the processor that okay, going forward you are going to get 16-bit instruction from the memory. So you are supposed to interpret whatever you read from the memory as 16-bit wide instructions, not 32-bit wide. Okay, that is what you are informing the processor. So how is it done? It is done by setting one bit in the register. Okay, let me come back. Now I said that BX instruction can exchange with some register. I am taking this example as R0. What exactly happens? Assume that this is at 100. Okay, and R0 is having 200, our favorite subroutine. Okay, now assume for a moment it is 200. Then what happens? This 200 gets written into R15. Okay, R15 is R0 is moved into R15. So what happens? The control flows goes to 200. Now during that time, what you can do optionally is in the RM0 bit. What I mean by RM0 bit, if suppose you are using R0, there will be LSB, right, for the register. Assume R0 is there, LSB bit is there. You know, in a typical ARM instruction, the last two bits are always 0, correct? Because it's a 4-byte aligned. But you are intentionally making this bit 1. Suppose you are doing, or maybe the assembler or compiler is doing. Now what the processor thinks, no, when it receives R0 and then it sees that LSB bit is set, then it will know, okay, now the programmer is interested in moving back to thumb mode. moving back or moving to. Okay, it doesn't matter. From ARM mode to thumb mode. That means what? Going forward, whatever instructions you encounter from the memory, please read it as 16-bit wide instructions. Internally process it as a 16-bit. Okay, you run it in thumb mode. It's a different mode of a processor. Okay, but only thing is it has to be communicated to the processor that it is going to be a 16-bit wide instructions. So that one will indicate to the processor that it is a 16-bit mode it is jumping to. So it will start reading from 200, 202, 204. Okay, you see the difference, 200, 202, 204, because it's a 16-bit 2 bytes. So 200 and 201 will correspond to one instruction, 222 to 203 will be another instruction, like that it will be interpreting it. So that is what is communicated by setting the lower LSB bit of the RM. Okay, I'm sorry, this should have also been RM. Okay, very good. So BX is used to switch between ARM and thumb mode. Okay, thumb mode will be discussed later in detail. Okay, don't worry about that. Now let me ask you one quiz. Take 2 minutes break. Read through this. Come back. Welcome back. You can find out how many people have different answers. Okay, you can see the distribution of the class. How many having these answers? I am sure all answers would have been picked up by you, or maybe only one. Hopefully that is correct one. Okay, this is A. Why? Just come back. Though this bit 1 is set, okay, it is ignored inside the processor. Other than setting the mode to thumb mode, T mode, the instruction will fetch from leaving the lower LSB bit. Why? Because all the thumb mode instructions are all 2 byte wide. So the similar to ARM mode, in ARM mode 2 lower bits are 0. Okay, in ARM mode 2 lower bits are 0 always, because it's a 4 byte boundary. In thumb mode, lower bit is always, the LSB is always 0. So the instruction address is only the remaining 31 bits. Please remember that. Okay, so what is the remaining 31 bit? Even if you expand it, it will not be any of them, right? It can't be this, because I said you have to go to 1000 only, so it can't be 1004. It can't be this, it can't be this, it has to be this only. Okay, it will just, though you are giving 1001, only the LSB bit is made 0 and then remaining value is copied into PC. So PC will move to 1000. Okay, I hope you are able to understand this. I explained a lot about this. So these are the 2 byte boundary addresses and these are the 4 byte boundary addresses. So if it has to be jumping to 1000, it has to be this address, not this one or any of this. Okay, good. Let us go. Again, we have a very interesting example. You can even take 10 minutes if you want. Please don't break away. This is the last slide of this class. So finish this and enjoy your day. Take a break, come back. Okay, welcome back. I hope you are able to understand what happens here. Let me explain. This is very trivial. Okay, I have put some instructions just to keep the processor busy and keep your brain also busy, so that no, it is not just instructions of our interest. I am just keeping some instructions. It doesn't have any meaning other than wasting the cycles of the processor. What is happening here? This is very important. You should not miss out this move. You can ignore these moves, but you can't ignore this, because is a very interesting register is there. So R15 gets copied into R0. Tell me what is the value of R15 and what gets stored in R0. You know, currently it is executing this instruction. Our PC will be here. So actually this address, please remember, R0 gets this. Okay, That's what I am saying here. Now the next point of interest is this one. What happens here? R0 is added with 4 and returned back into R0. Very straightforward. So it was having 1010. Please remember R0 is not modified anywhere here. So it is safe, intact. Whatever you saved here is there, which gets added to 4 by 4. So 1010 gets become 1014. Now what happens here? Bx R0. Now currently what I was saying 1014. So after this instruction, where will it jump? It will come here, correct? Because R0 was holding 1014. Now this will be executed. Now again it is going to execute this. At this moment 1014 was there, which will get added to 104, so it becomes 1018. Correct? Okay. Now when this BX is executed, the value of R0 is modified. It is changed now. So it is not going to jump back to this location like what it did. Will it come to this location? Agree? It will come here. Now what happens? Here again is getting added by 4. It becomes 101C. Please remember, it's all in hexadecimal. So what is 101C? Its own instruction, correct? So when this is executed, will it go anywhere else? Will it go anywhere to this area or this area, or will it stay here? It will stay here. So what happens in the processor is very funny, but it's interesting. Okay, BX gets executed here. Okay, and then at the end of the BS, R15 is loaded with the instruction 101C. So it will flush these instructions, whatever it has accessed, and then it will load again the BX instruction. Okay, so it will come here again. It will do the same thing. 101C is written into R15. So this processor is now locked onto this. It will never move to any other location. Forever it will be here. Agree? If you don't agree, read again. Understand this. If you don't understand this, go back to previous lecture, because this is the crux of what you learned in this lecture. Okay. In fact, it corresponds to something you learned earlier also, because you are seeing add and other instructions. So I'm sure you will understand this. Please run the same code in your simulator. Seeing is believing. Don't trust me. I may have given something wrong here. Please try it out. Try out the same set of instructions in your code and experiment it, understand it. Then you will be an expert in assembly programming. All the very best. Okay, that is what is done there. Now one more small example which I have already shown earlier. So ADR instruction, during this time, the last session I explained, ADR means it will copy, it will load the address of this particular label with 1. Okay, additional 1 is added to R0. Okay, where is this label? The label happens to be here. Okay, this label is here. So assembler computes the address and then adds 1 to that and then puts it in R0. Okay, now when this BX is done, the control comes here. At the same time, because you have set the B R0 bit 0 is 1, it moves to thumb mode. So it will execute all this as 16-bit instructions. Okay, and then it will execute BX R5. These are all thumb mode instructions, but these are similar to ARM instructions only. R5 is copied with back to ARM. Back to ARM is doesn't have a bit 0 as 1. It is 0 here. So once this bit is 0, it will know that this address is bringing back to ARM mode. So it will start fetching the instructions from here as 4-byte values. Okay, it will interpret them as ARM instructions which are set the bit right. So basically, I will come back to this again when I am explaining thumb mode, but I am saying that BX is used to change the instruction mode of the processor, instruction set of the processor. It changes from here it was ARM mode, it went to thumb mode, and then it came back to ARM mode. Okay, by executing this BX instruction by properly modifying the bit 0 of the register. Remember, this could be any register as long as that particular bit is, but register is loaded with the address of the instruction, this will work. So I hope this is clear to you. Even if you not understood fully, don't bother. When we talk about thumb mode, it will become much clearer, but it is part of the BX instructions. I thought I will explain you how the mode changes happen using these instructions. Okay, very good. We have come to the end of the session today. In this class, we talked about program flow, why it is required, why high level languages have a while loop and for loop and if then else, and how assembly can support those kind of control flow, and what are the timings, data path we saw in detail, and then we saw a few examples, and you have tried out also from a program as an exercise. So, and we saw how this helps in ARM to thumb mode, switching between modes. Okay, thank you guys, all of you, for your attention. I hope this was very useful. This is very interesting part of the discussion. So we will discuss again, come back again with some more interesting stuff on the ARM processor. Thank you very much for your time. Have a nice day. Bye bye.